So we'll finish up section 7.2, which is on a little bit more with inverse trig functions. And part of what we're going to do at the beginning of this section is take a formula, take an expression that has trig in it. We saw something like that in the homework last night, and get rid of the trig. Basically turn it into just algebra. So algebra means it doesn't have any sines, cosines, tangents, secants, cosecants. That's trig. Okay. A formula in algebra can have square roots, squaring, adding, subtracting, multiplying, dividing. It can have anything like that. But it can't have trig functions. So I'm going to show you how you take that and you can get rid of the trig. Okay, so this is basically called writing an algebraic expression from something that had trig. So the first step is we're going to start with the inner function. Okay, and when I say inner, and I'm looking at that question, I would say inverse cosine is the inner function. It's the one inside the parentheses. I would call sine the outer function. It's on the outside. And we're going to kind of forget about the outside function for a while. Okay, we're not going to do anything with it till the very end. What we're going to focus on first is the inner function. And what I want to do is set up a right triangle diagram. So I want to draw a picture of that. Now, I wrote this on the board when we did the homework. Whenever you do inverse trig, what kind of answer do you get? Yeah?
An angle.
An angle. So this entire thing right here is an angle. I don't know what angle this is going to be. Okay? And I'm not going to be able to figure that out because I have v. I don't have inverse sine or inverse cosine of a number. So I can't figure that out. When you can't figure out something, you usually use a variable. When you have an angle that you don't know, you're going to use a variable to represent it. But what kind of letters do we use in trig for angles that we don't know?
Greek letters.
Yeah, we usually use a Greek letter. So I'm going to let this entire red box just be represented by the Greek letter theta. So the inverse cosine of v is going to come out to some angle that I don't know. Let's just say it comes out to theta. Again, this sign has nothing to do with the question till the very end. So, any question why I said inverse cosine is going to equal some angle? All right. Now, I want to draw a diagram for that. But the way that you draw a right triangle diagram is not with inverse trig. You draw it with regular trig. So I want to take what we just wrote down, and I want to convert it to something with regular trig. That means I want to cancel out the inverse cosine. What function cancels inverse cosine? Yeah?
Cosine?
Regular cosine, yeah. So what we're going to do, and you have to do it on both sides, we're going to take the cosine of everything that's on the left, and we're going to take the cosine of everything that's on the right. What happens when you take the cosine of the inverse cosine? It cancels out. So now on the left-hand side, what do I have left? V equals, what do I have on the right-hand side?
Cosine of theta.
Cosine of theta. Now that is something I can draw a picture of. Think of cosine. What's the definition of cosine? It's what side over what side?
Adjacent over hypotenuse.
Cosine is equal to, I'm just going to put it off to the side, adjacent over hypotenuse. So cosine is equal to a fraction. Well, then let's make v a fraction. It's not a fraction. But how could we make it a fraction?
V over 1.
Right. We just put it over 1. So now look at what this is telling us. Since we know the cosine is v over 1, we're really getting two sides that we're going to label in a triangle. What two sides is the cosine telling us?
Adjacent and hypotenuse.
It's telling us the adjacent and the hypotenuse. What is it telling us about the adjacent? What is it supposed to be?
V.
It's supposed to be v. It's the adjacent. What is it telling us about the hypotenuse? Hypotenuse is 1. So now we've drawn a picture of what this red box is saying. We converted the red box to a picture. But we're missing something. What are we missing in the picture?
The opposite.
We're missing the opposite. Well, let's see if we need it. The function that they're asking us about on the outside is the sine. So this essentially means they want the sine of the picture you just drew. What two sides does sine use?
Opposite over hypotenuse.
Opposite over hypotenuse. I need the opposite. I need to figure that side out. But we have labels for two of the sides. So when you have two sides labeled, how can you find the third one?
Pythagorean theorem.
You can use the Pythagorean theorem. So temporarily, I mean, you could call this x. We're going to cross that x out in a second, and we're going to have a label for it. But let's call it x and figure out what it is. Okay, so how would I set up, make that so you can see it. Okay, how would I set up Pythagorean theorem with that, and that?
Yep. X squared plus b squared equals 1 squared.
And now solve it for x. How would you move b squared to the other side? Subtract it. And how would you get x by itself? Yep, take the square root on both sides. That's the formula for x. It's the square root of 1 minus b squared. I'm just going to put that right below.
Can that not simplify to square root of 1 minus b?
No.
Because you can't take a negative.
Yeah. If it was multiplication and you had something like x squared times y squared in the square root, yes, that is x times y. But when you change it to addition, then you got to leave it. Okay, so now we've got all three sides of the triangle labeled. Now the easy part is just to figure out what do they want to know. They want to know the sine. What did we say sine was?
Opposite over hypotenuse.
Opposite over hypotenuse. What's the opposite?
Square root of 1 minus b squared.
What's the hypotenuse?
1.
1. Figuring out those, that's the hard part. Once you figure them out, you just have to write whatever they want. Opposite over hypotenuse. Square root of 1 minus b squared over 1. And that is our answer.
This answer isn't very satisfying.
This answer?
Yeah.
Well, let's see if it works. If that's true, then that means you could put this in y1. You could put this in y2, and they should be exactly the same thing. The only difference between them is one of them uses trig to get your answer. The other one just uses algebra, squaring and square rooting. But it's exactly the same formula, if we did it right. All right, let's try it. Let's go to y equals. Yes, I'm just checking my answer. Remember, when you type in on the calculator, you always have to use x for the letter. You can't use anything else. Second, square root 1 minus x squared. Okay. Now, I'm going to go to my table. I'm going to type in some values, and I'm just going to check and see if they come out the same. Remember, inverse cosine has to be between -1 and 1. So you can give me any number you want me to check, but it has to be between -1 and 1. So what's a number that I could test? 0.32. If I plug 0.32 into the formula on the left, I get 0.94742. If I plug it in on the right, I get 0.94742. Each formula gave me the same result. Let's check it for, what's another number I could check?
0.
I could check 0. Both formulas give me 1. We could check one more. All right, I'll do -0.5. 0.866, 0.866. So these two formulas seem to always be giving me the same result, which means that they really are equal. And we can graph it too. If you set your window, I think if you do zoom 7, you'll be able to see it. That's the left formula, and that's the right formula. They're just small little graphs, but they are the same graph.
Mr. Hager,
Yeah.
something that just like blew right past me. How'd you get the hypotenuse of the triangle? How'd you determine that from v equals v cosine theta?
The hypotenuse, the adjacent was v, and the hypotenuse was 1.
How'd you determine that the hypotenuse was 1 though?
Well, I needed to make what they gave me into a fraction, and you can make anything a fraction by just putting it over 1.
Oh, so that principle alone automatically meant that the hypotenuse was 1.
Yeah.
Okay.
Yep. I'll give you another one where the hypotenuse isn't 1. But we'll try a couple more like this first. Yeah.
So where does the square root of 1 go in the...
Right here?
Yeah, so because you haven't taken the square root of it yet, is it just not copying it down, or?
Well, this was 1 squared, which just means 1 times 1. So I just made it 1.
Ah.
Yeah.
Thanks.
Yep.
So v would be equal to 0?
No.
What is v?
V?
Yeah.
V was the
No.
letter they
the
gave us.
actual numerical value of v.
Does it matter?
We're not finding a numerical value, we're finding a formula. So this problem isn't about finding a numerical value.
I know.
Yeah.
If you wanted to go further.
I don't think we could go any further. That's all you could do.
So you can't find the value because you have an equation.
No, because you have two unknowns in the same triangle. You have an x and a v. Yeah. So we're not really finding a value. We're finding a formula that replaces the trick. Okay, let's just try it. Try another one. The tangent of the inverse sine. So there's a way to do this calculation without using any of this trick. It's probably going to have a square root in it. Usually it has like a 1 and a minus, something squared. But we got to figure out what it is. So what function do we always start with? Start with the inner. And the kind of answer that you get when you do inverse trig, it always gives you what? It always gives you an angle. So what's inside that black box is going to be an angle. I don't know what the angle is going to be. I'm never going to know. So how do we represent an angle we don't know? Greek letter. Yeah, I usually use theta. Theta. T-H-E-T-A. Okay, so I take what's inside the parentheses. I'm going to set it equal to theta, because I know it's going to be an angle that I don't know. And now I want to rewrite this with regular trig, so I can draw a picture. What would I do on each side to get rid of inverse sine?
Take the sine of it.
Take the sine of both sides. So take the sine of what's on the left. Take the sine of what's on the right. And what happens when you take the sine of the inverse sine?
They cancel out.
They cancel out. What are you left with? V equals sine theta. Now again, you want to think of V as a fraction. Because what's the definition of sine? Opposite over hypotenuse. So this is going to be the opposite in my diagram. This is going to be the hypotenuse. What can you put to make v a fraction, but it doesn't actually change v? Just make it over 1. Yep. Okay, so now we need to draw a triangle where the opposite is v and the hypotenuse is a 1. Where you put theta, you can put it at the top, you can put it at the bottom, you're going to get the same answer. Your diagram will just look different. I usually just put it right there. Okay, so the sine is opposite over hypotenuse. What are we going to label the opposite? V. What are we going to label the hypotenuse? 1. Now let's go back up and look at the original problem. When everything's all done, they want to know the tangent of the diagram that we're drawing. What's tangent? Tangent is opposite, we got that, but we don't know the adjacent. So we have to figure out the adjacent using these other two sides. And what formula do we use to do that? Pythagorean theorem. So set up the Pythagorean theorem, and we're going to solve for x. Okay. What's the theorem going to look like when I fill in those three things?
X squared plus b squared equals 1 squared.
And now get the x by itself. All right, so how would we move the v squared over? Subtract it. And how would we get rid of the exponent of 2? Square root. I think we had something like that in the last one. That kind of comes up a lot. So the bottom is the square root of 1 minus v squared. Okay. Now we've got all three sides labeled. Okay. You don't need this x anymore. We just figured out what x is. It's the square root of 1 minus v squared. So now take the tangent of the diagram that you drew. So tangent is what again?
Opposite over adjacent.
Opposite over adjacent. Opposite over adjacent. V over the square root of 1 minus v squared. Now, technically, what's wrong with that? Square root's in the bottom. I'm not concerned about the square root in the bottom. All right, that's just one more thing we have to fix. So I'm gonna leave it like that. It's really not okay to leave it like that, but I'm okay with you leaving it like that. Okay.
So when I test those acceptable, right?
Yeah.
Okay.
So now let's just check it. We don't have to check it. Well, let's put the left in y1. So just tell us if we did it right. Inverse sine of x. Put in, just be careful, you're going to need some parentheses on the right. X divided by square root 1 minus x squared. Yeah, I think that should work. Let's hit graph. That's the left. That's the right. They look the same. A graph doesn't prove they're the same. But they pretty much look the same, and we proved it with the algebra. So I know that this formula is the same as that. Left side has trig, right side does not. Any question on that? Yes?
So not necessarily about this, but why can't we leave that on like that?
Why don't you leave square roots in a denominator in general?
Yeah.
I think because if you had something like this, and we know it's the same as this, when you're doing something by hand, I think for most people, it's a lot easier to do multiplication of a square root by hand than it would be to do long division with a square root. Multiplication is just an easier operation than division. That would be one of my guesses, if you had to do it by hand. With a calculator, fixing this so the root's in the bottom, I mean, really, what's the point anymore? I mean, I'm not sure. I think the only reason they still do it is just because it was something that they've done forever. I don't really know if there is a great reason. Now that we have calculators. Okay, is there any question on that one? All right, let's try. We're not going to do that one. All right. Let's try. Let's try this one. Now, this is pretty similar to the first two we did. Regular trig on the outside, inverse on the inside, but you're not going to need letters in this one. You're going to have all numbers. So let's start it the same way and see if we can figure it out. Since it's all numbers, you're actually going to get an answer. Right? You're not finding the formula because there's no variables in this whole problem. Okay, we're gonna have all numbers, and when we're done, we're gonna have a number for the answer. That's what a value is. Find the number. Okay. So which trig function do we always start with? Inside. Inside is an inverse trig function. When you do inverse trig, what kind of answer do you always get? You get an angle. Could be radians, could be degrees. We don't know. That doesn't even really matter right now. Okay, but we know it's going to be an angle. Do we know what angle it's going to be right now without a calculator? No. We don't know what that angle is going to be. Take what's inside. And how do we represent that we don't know that?
Set it equal to theta.
Yep, I'm going to set it equal to theta. Now I want to draw a picture of that. But to draw a picture, I need to get rid of the inverse trig. So it's the same thing every time. How do you get rid of the inverse trig?
Take the tangent of both sides.
Take the tangent of both sides. What happens with tangent and inverse tangent?
They cancel.
They cancel out. And what you're left with on this side is already a fraction. This is the spot where we usually have to put over 1. You don't have to do that this time. It's already a fraction. What goes on the right side?
Theta. I mean tangent of theta.
Tan theta. Now think about what tangent is telling you. What's the definition of tangent?
Opposite of adjacent.
Opposite over adjacent. So this is telling me two sides to label in a triangle. Draw your triangle. Put your angle. What does that tell me I should make the opposite?
1.
1. What other side does it tell me?
Adjacent.
It tells me the adjacent, and it tells me to make the adjacent 2. What side am I missing?
The hypotenuse.
Hypotenuse. I'm just going to call it C. And how am I going to figure it out? Yeah. What's the Pythagorean theorem going to look like with those three things I just circled?
1 plus 2 squared equals c squared.
1 squared plus 2 squared equals C squared. Okay, 1 squared,
1.
and then 2 squared. So that's 5. Remember, that's not C, that's C squared. And then you got to square root it. So what is C?
Square root of 5.
Square root of 5. Okay. So now we have all the sides labeled in the triangle. We don't have any variables for the sides. And they want to know the cosine. Okay. What's cosine?
Adjacent over hypotenuse.
Adjacent over hypotenuse. What's the adjacent?
2.
2. Divided by, what's the hypotenuse?
Square root of 5.
Square root of 5. And that is the exact answer. Again, I know the square root's at the bottom. I'm not worried about it. And let's check it. Take the cosine of the inverse tangent of a half. And now type in 2 divided by square root 5. 2 divided by square root. Now I messed it up. Same thing. So we figured out what it is. And the calculator won't be able to give you 2 divided by the square root of 5. And it's something you'd never be able to guess based on that decimal. It's just, you can't guess that. So you got to know how to figure it out the way I just showed you. Okay. Any question on that one? Yeah?
Yeah, so can you only solve these when there's more than one trigonometric function in the...
You mean like convert it to something with just algebra or a number like that?
Like, solve it without using the calculator. Because I can't see you doing the same thing with just, like, the inverse tangent of 1/2.
So there are ways to figure out when you only have one trig function. Yes, you can still figure it out. The formulas are something we don't get into in this class. It's kind of like getting into when you press sine 18. Like, how is the calculator actually getting negative 0.75? Like, what's the math that the calculator did to do that? You can do that by hand, but it's just not something that I ever show you. But so yeah, you can still do it.
So these, like sine, cosine, and tangent. So these aren't like numbers that sine gets multiplied by. There's like an entire mechanism behind them.
Yeah, there's a set of instructions the calculator is following to figure that out.
How long is it?
Well, it depends on how accurate of an answer you want. The calculator is accurate to 10 decimal places. So for you to get an answer accurate to 10 decimal places by hand, it may take you a minute or two to get that answer. You'd need a calculator to still do it because the numbers the formula to get that number can start to get pretty big calculations in it. But a computer can do it extremely fast.
Do you know the formula off the top of your head?
I know I think it's a Taylor series expansion formula. I'm pretty sure that's what it is. I don't exactly remember it, but I know it has to do with like evens and odds, adding and subtracting. And you just keep generalizing the formula more and more and more for the amount of accuracy you want. But yeah, it's not something we really get into. But yeah, you can do it pretty quick. Relatively quick.
On a question like this, where it's actual numerical values, would you be fine if it was either we write it as like the answer if we write it as 2 over root 5 or 2 root 5 over 5?
You could clean that up if you want as 2 root 5 over 5. You should clean it up. I won't take off points if you don't.
But in the case of the other one where it was also variables, you're fine just leaving it as is.
I'm fine both ways. If you want to clean that up, you can. If you leave it the way it is, that's fine. Because I'm not really focusing on fixing square roots in the denominator in this lesson.
Okay.
You should, but I'm not focusing on that. Let's try pretty much the end. Let's try one more. Let's try. Is there one we haven't done on the outside yet? We did inverse sine, I think. Oh no, we did regular sine. We did regular tangent. Did we do a cosine on the outside? Did a tangent? All right, let's do a cosine on the outside. Inverse
The last
cosine.
one we did was actually a cosine.
Oh, the last one was?
Oh, inverse cosine on the outside? We did regular cosine on the outside.
We did sine on the outside. We did tangent on the outside. We did inverse sine. Oh, we did. Well, okay. Well, let's just do cosine of inverse sine then. We'll just change it.
If you had an inverse trig function on the outside, would it be the same process?
Would it be what?
The same process?
When there's an inverse on the outside, it's a little different. I'm not going to get into it, but you can still do it, but it's not exactly the same. Let's try this one. Cosine of the inverse sine of square root 3 over x. What function do we start with? Inside. What do we set it equal to? Set it equal to theta. Now I need to rewrite it to get rid of the inverse trig. So what do?
Take the sine of both sides.
Take the sine of both sides. And what happens on the left? Cancels out. So what are you left with on the left? X. How about on the right? Sine theta. So now you need to draw a picture where you put an angle, and when you take the sine of that angle, it's root 3 over x. Okay. What does sine tell us? It tells us something about opposite over hypotenuse. So what should the opposite be in this picture? So that should be square root of 3. What should the hypotenuse be?
X.
That should be x. And let's go back up and see what they want. They want the cosine of this picture. What is the definition of cosine? Adjacent over hypotenuse. So we need to figure out this side. I'll temporarily just call it A for adjacent, but I'm going to cross that A out in a second when I use the Pythagorean theorem. Okay. How would you set up Pythagorean theorem with those three?
A squared plus 3 equals x squared.
A squared plus, don't simplify anything yet.
Oh, square root of 3 squared.
Square root of 3 squared equals x squared. Square and square root, those do cancel. And remember, you're trying to get A by itself. Okay, what would be the next step? Subtract 3. And the last step.
Square root both sides.
Square root both sides. Okay, so now we have a formula for A. It's the square root of x squared minus 3. All right, now they want us to do, what was it, cosine? Yep, take the cosine of that picture. Cosine is, what is it again? Adjacent over hypotenuse. What's the adjacent in that picture?
Square root of x squared plus 3.
Square root of x squared minus 3 over the hypotenuse is x. Yep. And I'm not going to check this one, but if you put what's on the left in y1, put what's on the right in y2, they should work the same. Yeah.
For the formula for adjacent being square root of x squared minus 3, does it matter which way you write it? Like square root of negative 3 plus x squared?
No, this would be the same thing. Kind of like saying 5 minus 2 and 2 plus negative 5. They are a commutative property.
Okay.
So that would be okay. Any other questions on how we got that? Okay. So, I think we've done enough of those. Okay. So the last thing, which is kind of a review, is how you solve trig equations on the calculator. Not as complicated ones that we did on, I think it was yesterday, 2 days ago, where you had to do like find the least common multiple of each term. It's going to be a lot simpler. It's going to be something like that. Okay. Or something like that. Just a single trig function. Trig functions, if you can find one solution, then they have infinite solutions. Say this is your first cycle, and you drew a line at like 0.5. How many times does that line cross the sine wave in that cycle? Yep.
2.
2. How many times is it going to cross it in the next cycle?
2.
The previous cycle?
2.
It's always going to cross 2 times. If you draw this forever, it's just going to keep crossing 2 times every cycle. So you have to find the intersect on the calculator here, find the intersect here, And then what do you put on the end to indicate that this answer repeats?
Plus TN.
Plus,
2 pi x.
yeah, whatever letter, we usually use 2 pi n. Yeah. You put a plus 2 pi n, or whatever the period is, plus the period times n. If you don't remember how to find the period, I gave you a chart on Tuesday where it had all the trig functions to an even or an odd power. So you can use that chart to figure out the period. Some trig functions we don't have a button for. So if I ask you to type in cotangent, there's no cotangent button. So how do you type in cotangent?
1 over K.
Right, you got to flip it. 1 over tangent. Same thing for secant. How do you type in secant?
1 over cos.
And cosecant?
1 over sin.
1 over sine. Yep. So we talked about these reciprocal identities. That was the lesson on Monday. That was the one where I think that was the hardest one. But it's just a reminder, you have to flip trig function to type it in. All right, so let's try this. Is this a trig function we have to flip? Nope. We got a button for that, so we can just type it in. Okay. What would go in y1? Sin x. Okay. What would go in y2? 0.6. Now we got to set our window so that it's exactly what? 1 cycle. So if you don't remember what the cycle length of sine is, you need to figure that out somehow. Use the chart I gave you. Gotta figure it out. That's sine to an odd power. What's the formula that we use when you have sine to an odd? 2 pi over b. B is the number that's in front of the x. In this case, it's just a 1. So what's the cycle length? 2 pi. So you need to set a window on your calculator that's exactly 2 pi wide. What could you use for a min and a max?
0, 2 pi.
Yeah, you can use any two numbers that give you a difference of 2 pi. I would just stick with 0 to whatever you need. How high and low does the sine function go? No, not -2 to 2. It goes -1 to 1. Well, we're going -4 to 4. That's more than you need, but that's okay. So when you hit graph, you should see exactly 1 cycle. You're going to have a line at 0.6. And how many answers do we get per cycle? You get 2. They want all the solutions. They don't just want the ones that you see on that screen. They want all of them. Even though I don't know what those 2 are yet, I already know what I'm going to put on the end. What are we going to put on the end of each solution? Right. You have to put the cycle length times n to indicate you get another answer every cycle. Okay, now I need the calculator to figure those out. So, okay, I'm gonna do the one that's kind of in the middle, and then if somebody has the one all the way on the left, that would be terrific. Okay, 2 pi is a radian. Make sure you're in radians. If you didn't want to do it in radians, you could have used a 360 instead. Okay, but we're doing radians. It's it's going to round up to 2.50. And what's the other solution?
0.64.
0.64. Okay. And that's how you find all solutions. If the question said, find all the answers, and it said to do this, does that mean they want all the solutions? No. It means they want the ones that you can see between 0 and 2 pi. So if the question said to find those answers, all you would do is write exactly what I have on the board right there, and you'd be done. Okay. but this one did say all. So you got to do it just like we had it right there. All right, and last question. Okay, cotangent x equals 2.5. All right, what's going to go in y1? What is it? Yeah, 1 over tan is one way to do it. I showed you another way on Monday, but we'll do with 1 over tan. That's fine. And what goes in y2? 2.5. Okay. Cotangent. What's the formula when you have cotangent to an odd power?
Pi over b.
It's pi over b. What's b in this case? 1. So what's the cycle length of cotangent? Pi. So I'm going to set my window from 0 to what? Pi. And that's going to show me exactly 1 cycle. Remember, this graph has vertical asymptote, so you're never going to see the top and the bottom of it. We don't need to. As long as you can see the 2.5, you'll be able to do the question. If you don't set your y max to at least 2.5, this red line is going to be off the screen. You're not going to be able to do it. Okay, so what do I need to do now?
Find the intersection.
Find the intersect. Second calc intersect. Then we get 0.381. Let's just say 0.3. Now, I did say all, so what goes on the end of that? Not 2 pi n. Pi n. Okay. Any question on that? All right, so let me put up the homework, let me check it, and then I'll put up the test topics. Okay, got it. That was good. Okay, so there's all the topics that are on the test. Okay, converting a trig expression to algebra, we did that today. Finding solutions graphically, we just did that today. Simplifying trig expressions, that was Monday. Evaluating an inverse trig expression, that was Tuesday. Finding domain and range of inverse trig, that was the homework last night. Okay, so those are the topics that are on the test. And I will be after school for extra help today.